Hi, my name is Rachel Pong. I'm at a summer program Cosmos in Cluster 3, and I will be talking about the dynamics of airplanes and the forces that act on the plane to make the plane fly. So first of all, air plays an important role in the flight of objects. It has weight and it's always constantly moving, and as the molecules move around, air pressure is produced, and force of moving air lifts the objects. There are four forces on the plane: lift, which is directed up; gravity or weight, which is directed down; drag, which is like a frictional force and it prevents the plane from moving forward; and thrust, which keeps the plane going and flying. First is lift. Lift is a mechanical force that opposes weight and holds the airplane in the air. The pressure of the air decreases as the air moves faster and creates different pressures above and below the wing. And lift is the difference in pressure which creates force on the lifting plane. The Bernoulli's equation calculates the air pressure, and you have to know the air velocity near the surface. Rho is constant density, and half of rho v squared is the dynamic pressure. And as the velocity goes up, the pressure goes down, and as the pressure goes up, the velocity goes down. When air flows over the curved surface of the wing, air is forced to move faster, so the pressure is lower on the top of the wing, and the air moves slower on the bottom, so the velocity is slower. Therefore, the pressure is higher. Weight is another force, and it's a gravitational force that all objects experience. The magnitude of the force depends on the mass of the object, and it's always directed towards the center of the Earth, even when the plane rotates. So it can be seen in Newton's second law of motion, F equals ma, or in this case, F equals mg, because acceleration is gravity. Talking about the plane rotating, the airplane rotates around the center of gravity, which is a point where the average mass is. From the center of gravity, there are three axes all perpendicular to one another: the roll axis, the yaw axis, and the pitch axis. And from the center, and when modeling airplanes, you need to take all three into account. The axis is the axis pointing down, and the motion of it can be seen as the nose moves from side to side. And next is the pitch axis, which is parallel to the wings of the plane. And you can see when the nose moves up or down, as seen when the plane is taking off or landing. And the last one is the roll axis, which is which is parallel to the body of the planes, and you can see the motion of the plane when the entire plane is moving side to side, like when the wings are tilting and the entire plane tilts one way or another. Next is drag. It's a mechanical force which is generated by the difference in velocity, creating friction that prevents the airplane from flying forward. It depends on the size of the object, the square of the velocity, the density of the air, and the viscosity and compressibility. The friction, also called the skin friction, is between air molecules and the surface of the airplane. So if there's a smoother surface, there's less skin friction, and if there's more a rougher surface, there's more skin friction. The drag equation is d equals cd times rho v squared over 2 times a, which c sub d is the drag coefficient effective when choosing the reference area, and the magnitude of the force depends on the viscosity, and viscosity is the measure of fluids resistant to flow. The viscosity is tied to the Reynolds number, and the Reynolds number is the ratio of inertial forces to viscosity. In other words, it's the resistance to change in motion to friction forces. The inertial force is rho times v times dv dx, which is the density times velocity times the gradient of velocity. And the viscosity force is mu times the second derivative of velocity with respect to x, which is the viscosity coefficient times the second gradient of velocity. Last is the thrust force, which is mechanical force that moves the airplane through the air, and it's used to overcome drag. It's generated through the engines, and the direction of the thrust is based on which way the engines are directed. Thrust is aligned with the direction of flight and its opposite airflow. So the impact planes have had in the world is that now it has decreased travel time by a lot, and you can travel basically anywhere in the world and visit family or go on vacation.
You quoted the wrong tail. You have to get rid of this tail.
Next is, I will be talking about my mathematician and scientist Lagrange, Joseph Louis Lagrange and Lord Kelvin, and a few of their math and science contributions. First, Joseph Louis Lagrange. He's an Italian Enlightenment era mathematician and astronomer who contributed to analysis, number theory, and classical and celestial mechanics. He is a mathematician who focused on calculus, and he's known for his Lagrange error and the Euler-Lagrange equations. So he's known for his Lagrange error, which finds the highest possible value of the approximation and can be from the actual function. It's the difference between the function and the approximation. And the first equation is the Taylor series polynomial, and the second equation was the Lagrange error equation. So C is the polynomial center, N is the degree of polynomial, X is the number being approximated, and Z is the number between X and C. So you need to find the maximum of the nth derivative of the function f of x to maximize it as much as possible. Next, I will talk about the Euler-Lagrange equations, which is a differential equation whose solution are the function for the given function is stationary, and the differential function is a stationary at local maximum or minimum, and it's used to solve optimizational problems. So the final, the equation is a function of many different equations, L of t of x of v, and where x is q of t and v is q prime of t. And the final equation is the partial derivative of L with respect to x, and it's equal to the first derivative of the partial derivative of L with respect to v. And next I will talk about Lord Kelvin. He's a scientist. His real name is William Thomson, and he's a mathematical physicist and engineer who formulated the second law of thermodynamics, or helped formulate it. He contributed to thermodynamics, and he's most known for his Kelvin scale, where he found the absolute zero, and the Joule-Thomson effect, and the Kelvin-Planck statement. So he created the Kelvin scale to start at 0, which is defined as absolute 0, so that there are no negative temperatures. And he designed it so that all three of the phases, solid, liquid, and gas, exist at the same time in thermodynamic equilibrium. That point is called the triple point, where water is 273.16 degrees Celsius, 273.16 kelvins, also equal to 0 degrees Celsius. So the graph is a phase diagram, which shows where the distinct phases can occur at equilibrium. And based on the temperature and pressure of the element, you can tell whether the element is a solid, liquid, or gas. Next is the Joule-Thomson effect, where the change in temperature that accompanies the expansion of the gas without production of work or transfer of heat. And at normal temperature and pressure, all gases but hydrogen, helium, and neon cool upon expansion by the Joule-Thomson process because of the Joule-Thomson coefficient. As molecules move farther apart, work must be done to overcome the long-range attraction between them, and so cooling occurs. And hydrogen and helium will only cool only if their initial temperature is very low because long-range forces in them is weak. So the Joule-Thomson coefficient is the rate of temperature T with respect to P in the Joule-Thomson process, and the coefficient can be expressed in the gas's volume V overheats constant pressure C sub P and the coefficient of thermal expansion alpha. So the figure below is the Joule-Thomson coefficients for various gases at atmospheric pressure. As you can see, helium and hydrogen have low Joule-Thomson coefficients. So lastly is the Kelvin-Planck statement, where also called the heat engine statement of the second law of thermodynamics, which states that it's impossible for the heat engine to absorb heat and transform it all into work. In other words, it says that it's impossible for a heat engine to be 100% efficient.